Hello and welcome to the KIM-1 Corner, episode 10. In this episode, we'll be starting to look at this solid-state drive that I've designed for the KIM-1. Before we get into the details of this, let's look at the reasoning behind it. So we've got a bit of a problem of how can we easily save and load data and programs to the KIM-1. We can do it over the serial port, but that is relatively slow. It could take us minutes to load stuff in. I thought, well, maybe we could build some sort of solid-state drive. Well, I've already started writing stuff in the monitor program, so if we have a little look at that, we've got this list here. Now you notice there's a save data, load data, list files, delete files, and there's this read page and write page. They're special ones, we'll come to them in a short while. So if we just wanted to save a block of data that's on the KIM-1, we just select the first menu, and it asks us where we want to start from. So you put the address in, might start from address 2000, and we want the end address, so we might be saying like FF, that's 512 bytes of memory there. Then we give it a file name, so we call this, I don't know, test if you like. Press enter, and that should go off and save that. It's not actually doing that here because I haven't actually got the card plugged in, and it's I'm still working on software. But basically, we just want to be able to save and load files. The memory areas that you'd be saving, they could be actual programs or whatever you like. Now, we could do this with an SD card. I mean, there's many interfaces built out there with SD cards, but then you've got to start dealing with FAT32, etc. And a DOS FAT system is a bit heavy for what we want to do. It's quite a bit of loading on reading and writing to it, and I didn't want to load up the KIM too much. I thought I'd design my own one and make quite a simple interface between the KIM and the actual solid-state drive, and push off the loading of all the file system, etc. onto a microcontroller that's going to control everything. We just do requests like save this or load that. While looking around at different ways of doing this, I looked at SD cards, and as I say, the FAT32 was a bit complicated. So I come across these. They're just a simple EEPROM. It's a serial one, and this one here is 32 megabits, which is 4 megabytes. And that'd be more than enough for the KIM. We can save plenty of files on there. And it's got this page size of 512 bytes. So that's basically like your sector on a disk drive. We could ignore all the other ways that it does things. We will just be looking at these pages. I'll refer to them as pages all the time because they are like sectors, but the documentation says pages all the time, and then a sector on this IC is 4K. So it could get confusing, so we just call it pages. This is the smallest size chunk of data we can access on this IC in one easy hit. We scroll down, here's the actual IC, so it's just a simple little 4-pin. We'll only be using 6 of these. We'll be using obviously the supply ones, and this is a chip select, we want that. Then we'll have this one here, this is the data out, D0. On Q here, that'd be the data in. This one here we won't be using. That's either write protect or data 2 out. You can actually read 4 bits at a time out of this. We'll only be doing 1 because this is going to be running a lot faster than the KIM anyhow. So it won't really slow anything down. And we've got this hold signal here. So this hold signal and this write protect, they'll be held high all the time. We just use the chip select here for selecting it. Now if we scroll a bit further down past all this stuff, we just need to know that it's all done in these pages. You've got 8,192 pages, and each one holds 512 bytes. So this is sort of how we'll be having it. We'll only have one device, and then we'll have a controller using SPI to control it and push the data in and out. So this will be the microcontroller on the board, and this will be the EEPROM itself. SPI mode to talk to it is easy, just a simple clock on and off and data in and out. We'll go through all this in more detail in a later episode. Okay, if we just look at write in a moment, because that's where it is, you enable the write by sending this command, and then you can write data. So it's always protected from writing unless you specifically tell it to. So this is like the read command. We just send it a number 3 and the address of where we want to start reading. Now this is all addressed in individual bytes, so it's a 24-bit address. We send that in, and then we send more clock signals, and it pulses out the data at that point. We can read 1 byte, or we can just carry on reading the whole IC if we wanted to. So normally we'll be reading 512 bytes at a time now. One nice feature of this IC is we've got this page write command. Normally you'd have to erase the page you want to write to and then write to it, but this has got it all built in, so we can use this command here and we write a page of data. It's got 1 page buffer built into the IC. So we write a page, so there's like a write command with address, so we send the data and the address will automatically increment, so we just keep sending bytes of data to it. So we send 512 bytes of data and then finish the command, and it will do the erase of that block for us and then program it. So we don't have to worry about doing any erases on the IC at all. It's all automatic. So if we have a quick look at the circuit diagram, we'll go in this in more detail on another video. We've got, here's the EEPROM down here, and that's fed onto this microcontroller here. We'll talk about that one later. And then we've got these 4, zoom out a bit, you've got 4 bus ICs. And they've got this bus here on board, and this is the usual KIM interface for the cards. So the KIM talks through here and puts data onto these 2 ICs here, or reads data via these 2 ICs. So that's how it communicates back with the microcontroller. These other chips down here, that's just logic gates for working out the addresses. We'll be working at address 1600 and 1601. 1600 being the data coming in, so that is either that'd be a whole byte, so it'll either be a data byte or a command. And then this one is sort of like a control at address 1601, where certain bits mean certain things. I'll put the data on here and then turn these bits on and off, and the microcontroller will be scanning these ports. So that's how we transfer the commands. And when it replies back through these using the same address. Writing goes to here, and reading comes from there, and so forth. And this will switch between them as necessary. So here's a simple block diagram of how the system will be working. We have the KIM bus, which is just that big 60-way edge connector that we got. And then you've got controller IC here, be a microchip controller, that's doing all the data communication backwards and forwards and actually saving the data to the EEPROM. Now the interface between the two, which is what we'll be covering in this video, covers these 4 ports here. Now these are actually these 4 ICs you see here. So this one here has got the control signals going in, and this one's got your data going in, and these ones got control signal back, data back and control back. So these use my favourite ICs, the 74573s, and the KIM can latch data into these at any time it wishes. And the microcontroller here will normally be scanning this to see whether there's anything coming up and then acting upon it. And when it's got anything to send back out, it puts it out on these, it will put the data out, and then it will put on the control here that there's data ready to be read. So that can write to these any time it wishes and they get latched in. So when this wants to read these, there's an output enable it can read, and when the KIM wants to read these, again there's an output enable going in that direction. So you may notice the ICs are actually physically up the other way. Yeah, and this stuff here, that's just the logic for working out the addressing, etc. You'll also see this port here, which is a serial port, so we can plug it into a PC and actually talk to this EEPROM and this microcontroller separately. We'll cover that in another video as well. So if the KIM wants to send a command, we go to the next slide down, it's got these bits in that bottom control byte. So this control here, data, the KIM will put, if it's going to send a command, it's going to read something, it will put the command for read onto the data byte. It will then go to the control byte and it will put this bit on. Bit 0 will be turned on to say it's a command. This will be set to 0 because it hasn't read any data at the moment, and all the other bits will be 0. You'll set that first, and then it will set this flag here to say that there's a command ready to be read. I should do this one last because the KIM is running at 1 megahertz and it may take 2 or 3 microseconds for the data actually all to get put onto here. And you've got rise time and the pulses here we've got to be careful of. because the microcontroller is running at 100 megahertz, and that's doing one instruction per cycle. So that's 100 instructions per microsecond. So this could be scanning and going back out before this pulse has even risen. So we put all the controls on there apart from this command. Keep that at 0. Put them all on, and then turn that one on in a separate command, because we'll just be scanning that one bit with the controller. If we put them all on at once, this line here could go high before the others do, and thus it could misread it. So where you've got this command bit here, this bit might get read before this bit, just purely because the pulse coming in isn't a straight line. They've got a slope to them. And this is an asynchronous interface, so you're just waiting for the pulses, like OS232, really. So you've got to make sure that bit's done separately to make sure everything else is ready first. So we would have put command on here, and then set the control here with that last bit coming on, very last bit, and this is scanning that bit, and you go, oh, I've got some command or data coming in, and then this will read what that is and act upon that, and then send anything back that it needs to. And we'll go into that on the next one. So here we've got the control for the microcontroller sending out. That's this one up here. I can put a bit on here saying the data has been read, and the KIM will be monitoring this port here to say, okay, it's received the instruction and it's doing something with it. So here we are from the KIM bus side of things. This is what the KIM's going to be sending out. Now it can send these different commands, and what it do is it put the command into there and then set the bits to say there's a command ready to go. So we can read a byte, or we can open a file to read, or we can close the read file, or we can read the header of a file. But there's this sort of write byte command. There isn't really a write byte command, because the way data gets transferred backwards and forwards, one side knows that there's data coming in here, so you don't actually, there isn't a command saying write byte, you just actually put a data byte out, because the solid state drive will be ready for it anyhow. But then there's open a file to write. It's different from opening to read. And then there's close write. Now when you close a file you've been reading, you just abandon everything and go back to the beginning. But if you're closing a file you're writing, you need to actually write the data, the last bits of data, to the actual drive. The open for write and open for read are not the same thing. Then you've got delete file. If there's a file you don't want, so you do get file name, etc. Then there's list files, where you can list all the files on the drive. And then there's a read status command. That's to let you know that a file has been saved correctly, etc. There's different things that can come back through there. So whether a file has been opened or not, so when you tell it to open a file, we need to come back and say, yes, I've opened a file, and this needs to read the status to see that it's done it. And then there's these two commands here, which is read page and write page. They can be quite dangerous, the write page, because it just writes whatever you say, wherever you say, and you can totally corrupt everything. But basically, everything works on reading pages and writing pages, as we'll see later. From the solid state drive side of things, where it's putting controls out, you don't just say, yes, I've read the data in OK. You've got to say there's other things as well. You can have error commands come through. When you're communicating back, as we'll see in the handshake bit, how the communication comes back, you put your data or error code in the data, and then on the control part of it, you've got this bit here says you've got data ready to be read back, or an error code ready to be read back. And bit 2, as we saw earlier, to say that you'd read the command earlier, or data to let you know that's needed for the handshaking. And then you've got this bit 7 at the top. If that's set, then it means you've got an error. So here's your 3 status. Here's 0 just means, yeah, okay, we're ready to go. 1 means a file has been opened, and 2 says, yes, that file has been deleted if you'd asked for delete. Now all your error codes are up the top end, so that's -255, -254, etc. Higher numbers are error codes, and we've got a selection of those. So you've got end of file, which is a sort of a semi-error. You may be looking for an end of file because you just want to read all the data. Then there's file not found, if you're trying to open a file and you can't find that file name. Now the disk can become full, so you need an error code to say that the disk is full. You can't write any more to it. And there's file full. We'll cover this on another video where we cover the file structure. There is a limit on the size of the files. and this file not opens when you're trying to read data, but you haven't actually opened the file yet, for whatever reason. And then if you're saying you're trying to save a file that already exists, so you need to be known that no, you can't save under that file name, it's already there. And then this command error means it just didn't understand what you said. The command got garbled all the way through. Something's gone drastically wrong. So this is the handshaking. This is an asynchronous system, so they need to talk to each other backwards and forwards to say they've read the data, etc. It's a bit like your clear to send and request to send in serial ports, but everything's being transferred in whole bytes at a time. So the solid state controller here, solid state drive controller, is continually scanning the KIM control byte to see whether any data has been set. So it's looking at one particular bit. It's looking at this set command ready flag. So the KIM, when it wants to send a command, it'll put the command in the data byte and then puts whatever bits it needs in the control bytes on, and then it will turn this last flag on the control byte on. As we mentioned earlier, we've got to be careful of the timings of the rise times of the pulses, etc. So that's the very last thing it does. It puts that on, and then the KIM will go off to scan the solid state drive's control byte, which should be at 0 at the moment. Anyhow, so the solid state drive has seen this bit come on. It reads the data, or in this case a command, from the data byte, and if it is a command, it starts that command. Now, depending on the command, you may do the command and return the handshake, or it may just start it. So if it's going to be reading, say, a file, it needs to know things like file names, etc. So all it can say is, yes, I'm starting that command, I've read the command. So it sets a bit on its control byte that the KIM is scanning to say, I've read the command coming in. So here, this command here says command or data has been read. These other bits will be off. So if there's no errors, that'll be a 0, and there isn't any data or status code to be read, so that'll be 0. So it'll be just that one bit there. When it turns that on, saying to the KIM, yes, I've read your instruction. So the KIM goes, okay, it's read the instruction. This handshake is the same for data as well. So it's either read the instruction or it's read data. What the KIM then does is it clears its own control and data bytes. The ones it's set up here, it's now going to clear it, because once the solid state controller has set, yes, I've read your command, it needs to know that the KIM has seen that it has read the command. It is scanning the KIM control byte to see whether there's anything there for it. The KIM here sets it to 0, clears the KIM control byte and the data byte. So this is looking for 0. When it sees 0, it goes, yes, the KIM knows that I've read the command and I'm starting the command. Conversely, over this side where the KIM is cleared its control, but it needs to know that the controller has seen that it's cleared its control. So it's going to scan the solid state drive's control byte again, as it did here, and this time it's looking for a 0 to be there. On the solid state drive, it says, I've told the KIM that I've read everything, and I've seen that the KIM has seen that I've said that, so I'm going to clear my control byte to say, yes, okay. And the KIM's watching that, and when he sees that, they've all gone back to 0. The KIM knows that the control's all been read. So to recap that in a simpler way, KIM puts the command out, controller reads it and says, yes, I've got that. And KIM goes, great, I'll put a 0 out to let you know that I know you've got it. And the controller then goes, oh, there's a 0, I know he's got it, I'll put a 0 out to let the KIM know that I know that he's got it. So the KIM goes, yes, he definitely got that command, everything's okay. I can go back and do the next bit while the controller gets on doing whatever it has to do. There's just a little bit in between that if it can actually perform the command, it can say good or bad on it. So you can have a 1 byte whole command, everything's done in one go because you've got that error or status return part of it. Oh, a little bit involved, but as you see, it becomes more apparent later. So if we want to open a file to read it, the KIM will send command 2 over here, telling the solid state drive that he wants to open a file. So the solid state drive has been scanning, receives the command, and it then knows from the command 2 that it needs to receive a file name after. So after it's told the KIM that it's received the command, the KIM will then send the file name, which will be 16 bytes long. The actual name can be shorter than that, and it's just padded out with spaces afterwards. So that is then transmitted 1 byte at a time to the solid state drive. And once it's got the file name over there, it then goes off to see if it can find the file. And if it can, it sends back to the KIM saying it's found it, that the file is open, or there's some error like it can't find the file. So is the file open? If not, then it will just get an error message. If it is open, then it can check, go further on, as in where is it going to load it to. Whereas on the solid state drive here, it's just waiting for the next command. So actually reading the bytes, the KIM will send the read byte command, which is command number 1, and the solid state drive will receive that command. If it's a read command, then it gets a byte and sends it, puts it in the data from the solid state drive, and sends a command saying there's data ready to be read by the KIM. Then it just goes back to 1 and wait for a command again. So we just keep looping here. Then the KIM basically just keeps looping around here, reading all the bytes that it wants. Now the actual file, the first 2 bytes read across when reading, won't actually be the file. There'll be the start address of where the file should go. Now whether you use these or not is down to the user. If you're saved like a program, you want the program to load it back into the same place in memory. So the first 2 bytes coming back is where it was saved from, so you can drop it back into exactly the same place. If it's just a data one, then you could ignore that, or you can load it wherever you want. You can actually put the address in there where you want to read it to. Now, of course, it checks to see if there's an end of file, because you may want, it might be like a data file and you don't know how long it is, so you just keep reading until you've hit the end of file. Then when you're finished, you can send a close command to here. So it won't be a read command, it will be a close command. If it's close command, it will jump to the part of the sequence that's just receiving new commands coming in, as in close the file. So from the KIM's point of view, all it has to do to read a file is send a command number 2, which is open for read. It will then send 16 bytes of the file name. Then it will send a command number 12, which is read the status. If it's a 0, it just keeps looping. If it's not a 0, then something's happened. It's either an error or it's opened the file. So if we get a 1 back, yes, the file is open. Then the KIM reads 2 bytes in. If you'd saved the file from a certain location, it will have that address saved in there in the header. So when you read it in, you know where to put the file. If you want to, you don't have to, you can save it wherever you want. That just makes it nice and easy if you're like loading a program back in to make sure it goes in the right place. It then starts reading the actual file. So it's going to read 1 byte at a time for however many it wants. There is a file length built into the data header, how long it is. And when you reach the end of it, the solid state drive will actually send an end of file. If not, you just read 1 byte at a time and put it wherever you want it. If you know how long it is, then that's fine. If not, you just wait until you get end of file and know you're finished. So it then just sends command byte 3, which is close it. Now, writing a file is very similar. KIM will send a 6, which is open to write. Solid state drive will receive that command, and if the disk is full, it will put an error back to say whether it's full or not. If not, it will send a 0 back saying, yes, okay, received your command, off you go. The KIM will then send the file name. It's 16 bytes long, so I want to open a file for writing to with this file name. The solid state drive will receive the file name, and it will check to see whether it exists or not. If it does exist, it will send an error back saying file exists. Okay, so at this point here, does the file exist? You'll be using the status command, or the KIM will be using the status command to tell whether it's okay or not. And if the file's okay and it's created, off you go. If not, it just return an error. If the file's okay, the file's been created, we've got to start sending other data. So the solid state drive now is waiting for the start address, as mentioned before on the read, where it reads the start address here. When we're doing a save, we need to send it to it. So if we're saving a file, when you do the save on that menu, you've got to tell it where to go to. So that address where you're starting from will be sent to the solid state drive, and that will be put into the header as the starting address. Solid state drive now will open the file buffers, as in it will create a file allocation table, if we go through the next video, for where data is being saved, and it will start the length counter, so the file length. And then it will wait for more commands, or rather it's waiting for bytes to come in normally, but it'll be checking the commands as well. So we actually write stuff. So you see the solid state drive has to do quite a lot here. KIM, when it says write bytes, it's not using the write byte command. As I say, it doesn't really exist. What it's doing is actually just putting byte of data and saying there's a byte of data ready. Solid state drive will read that byte in, assuming it's a byte command, because it could be a close command. It's just receiving that byte. And if it is a byte, then it saves it in the buffer. Updates the length counter. The buffer is full. We've got 512 bytes there. It needs to write it to the solid state drive. So it actually writes it and then clears the buffer, waiting for some more data to come in. And once it's actually written the data out, it has to update the file allocation table. And we've got this thing called a page usage data. We'll cover all that in the next video as well. That bit there pretty much controls where everything is on the drive. Anyhow, solid state drive, go back to number 1 and keep looping around as the bytes are coming in, and the KIM will just keep sending bytes. And if it receives a close command, or basically any command really, but if it's a close command, it goes, right, I've got to close. Any data that's coming in going in the buffer, it needs to write that out, then needs to update the file allocation table to say where it saved it to, and the length of the file, and this page usage data again. So it updates all that, writes those to the drive, and then jumps back out to wait for a new command to come in. In the middle of this, you could have the file fill up. You've only got 122 kilobytes maximum file size. If that fills up, what it does is it writes all this out and tells the KIM that that's it, the file is full, and then the KIM software's just got to deal with that. From the KIM's point of view, send command number 6, open a file, send the 16 data bytes, the file name, and read the status to say that the file's been opened or not. It's been opened, then send the 2 address bytes where the file was coming from, memory location it was coming from, if any, otherwise just send zeros. And then send the actual data, however many bytes that is. And then when you're finished, just send your close command, and that command then makes sure everything is finalized and written to the disk drive. So from the KIM's point of view, quite straightforward, quite similar to the read one. Instead of reading bytes, you're writing bytes. So if you want to delete a file, again, you're just sending a command. So command 10, delete a file. And then you've got to send it what file name it is, and it receives that. Then it goes off to find the file. If it can't find the file, it just kind of sends a message back saying, I can't find that file. That's the end of it. If it can find that file, then it updates this usage page, which basically marks it as deleted. And there you go, job done. Nice and simple, that one. So from the KIM's point of view, it says command 10, delete, 16 bytes file name, and then just checks the status at the end, which will tell it whether the file's been deleted or not. And we've got list files, so get a directory listing. So command 11, send the command 11, solid state drive goes, oh right, got command 11 to list everything. So it reads the file allocation tables, the headers on it, converts the file length and the address where it is to text, and then just sends them out as bytes, as if it's like you're reading a file. So you're just reading bytes here until you get an end of file command. So this just keeps spilling them all out until it's run out, and then you get an end of file, say, yes, that's the whole list, and the KIM just stops. So end of file isn't an error there, it's just telling you that's the end of the list. So from KIM's point of view, sends in 11, and then just reads loads of bytes in until the end of file. Now we've got the read and write page commands. The PC interface will use these quite heavily, but the KIM doesn't really need to use them. And the read is fine, but the write can be quite dangerous. So reading a page, command number 14. I just want to read a page of data. I'm going to tell you exactly which page it is. So the solid state drive has got 8,192 pages on it, and you can read them individually. Each one's 512 bytes long. So just send a command 14, solid state drive receives the command, and then you've got to send a page number. So there'll be 2 more bytes with the address of which page you want to read. So it's like page 1, it'll be 01, or it'll be 0001, and you just send 2 bytes of data to say this page number, and it will get the page number, and then it will open the page and start reading in the bytes, and you've then got to do 512 reads to get your 512 bytes. You don't have to do all 512, you can just read some of them and then just send a different command which then this will see there's a different command and jump out of this. If the solid state drive receives an unexpected command, it will try to cope with it, and basically if you say you're reading or something, it just forgets what you're doing and jumps back to the new command. Try to make it a little bit robust in case things go wrong. So read a page from the KIM's point of view, send a number 14, send which page in 2 data bytes, and then read how many bytes you want, straightforwards. So read a byte is command number 1. So if you want to write a page, now this one is very dangerous, there's no error checking or anything. You can easily destroy the formatting of the data on the solid state drive with this. You could use this to basically format the drive, which you shouldn't have to do anyhow. You have to configure it to start up, and we do all that on the PC anyhow. So command 15 is write a page. So solid state drive receives that, what page number you want to write. So you've got your page number you send, and then it creates a buffer, 512 byte buffer in memory, and you send it 512 bytes. Once it's received those 512 bytes, it then writes that page. And that's it. So you can, if you pick the wrong page number, so you shouldn't write anything to first 16 pages, because if you do, you'll totally corrupt everything. So if you did put the wrong page number in there and you got your bytes in, you'd overwrite the usage table, and you won't be able to find any files after that. You'd totally corrupt it all. And there's no close, you just send 512 bytes, and that's it. So simply, you send command number 15, then page number, and then 512 bytes. That's there to allow you to do pretty much anything on the drive. You're just reading and writing pages to the solid state drive. It gives you flexibility to do things. Don't use it unless you know what you're doing. Well, that's basically these 6 commands here. Only really need the top 4, as in save data, load data, list files, and delete file. I'll also be integrating this load and save into the Microsoft Basic, so that you could load and save basic programs direct within the Basic. Those commands are not actually implemented within Basic itself. Save all this trying to list it out and read it back in slowly. In the next video, we'll cover how the file structure actually works. Our simplified version of a FAT32, just don't know what to call this one. No, KIM DOS. But we go through that, and then in the video after that, we go into more detail of how the microcontroller actually pushes and shoves things around. We won't actually be going too detailed into the code of the microcontroller. Be more of a sort of a block diagrammy thing, not too much in the code. And it'll show you how to handshake back to the KIM and how you get things synchronized up and how it reads and writes things, and how you talk to the EEPROM. I actually done the SPI by bit bashing because working out how to do it on the controller was taking more time than it was worth. And there's also a basic program that we can look at the EEPROM with. So we have actually got this basic program here where we can read and write pages and get all the data in here. And this can be expanded to do even more things where it can actually look at the file structure, etc. This will be expanded to enable you to read and write files direct from the PC to the EEPROM, and thus be able to pick up by the KIM to read in using this program. To be read in using the monitor here. A way of getting your data on and off the KIM simply. So don't forget to like and subscribe, and not only covering those bits in the block diagram, but we'll have a little bit closer look at the circuitry, how these are switched on and off, etc. Try and make the next episode not quite so heavy as this one. So that's all for now, and I hope to see you in the next episode.